Hello everyone. So we have a question here that says the observation of equal CuO distances in the hexa-coordinated Cu2 complex K2Pb Cu NO2 whole 6 is best understood in terms of. So we have four options and we have to predict that which is the most suitable option for this situation. So option A says failure of the Jahn-Teller distortion theorem to predict the structure of this complex. Option B says error in the crystallographic estimate of CuO distances. Option C says dynamic Jahn-Teller distortion of the CuO bonds. And option D says symmetrical distribution of the 9 valence electrons of Cu2. Okay, first let's understand what the question is trying to say. So in this question, basically we have this complex K2Pb Cu NO2 whole 6. Okay. And the question itself says that copper is in the +2 oxidation state. So first of all, what we have to do is to get the valence electronic configuration of copper. So in the ground state, copper is 3d10 4s1. And what happens to copper in the +2 oxidation state? It becomes 3d9 and 4s0. So we have d9 electrons. So basically, this question is about the phenomena of Jahn-Teller distortion. Okay, so Jahn-Teller distortion, if you recap, when does that occur? It occurs when there is unsymmetrical filling of T2G or EG orbitals leading to the deviation from the regular geometry. Okay, and if that Jahn-Teller distortion occurs, then any of these bonds in the octahedral complexes, mostly the axial bonds, either they are elongated or they are shortened. So you can recall Z out and Z in situation if you read the theoretical aspects of Jahn-Teller distortion. So here also you can just recall the octahedral structure. So we have 6 NO2 ligands. So copper is in the octahedral geometry. Okay, so we have these 4 equatorial positions and 2 bottom and top axial positions. So it says the metal ligand bonds, the bond between Cu and NO2. So CuO bond it is saying, right? CuO bond means NO2 is like O and O here, right? Okay, so the ligands are coordinated with copper like this, okay? ONO, ONO. That is why we are specifically being asked about the CuO bonds. So this is the linkage like this. So it is being asked that whether due to this Jahn-Teller distortion, whether any of these bonds will be longer. So basically what happens due to Jahn-Teller distortion, mostly the axial bonds, they either elongate, okay, or they shorten, okay. So this kind, so L here is ligand. So I am showing you a picture where there is, if there is Jahn-Teller distortion, either these two axial bonds are elongated or these two bonds are shortened. That means these axial bonds are of different length as compared to the remaining 4 equatorial bonds with the central metal ion. Okay, so we have to answer the most suitable statement that instead of getting longer or shorter, why these axial bonds, the CuO metal ligand bonds at the axial positions are of equal length in spite of the copper in the +2 oxidation state showing Jahn-Teller distortion. So we know very well that if there is a D9 situation, then obviously that will be an unsymmetrical filling of the EG orbitals like this, okay. In any case, high spin, low spin complexes, D9 is always an unsymmetrical filling of the EG orbitals and it shows Jahn-Teller distortion, okay. So obviously this D9 configuration gives us the Jahn-Teller distortion. So there is difference in the bond lengths along this axial bond axis. So one of them is a longer bond or shorter bond as compared to the equatorial bonds, the remaining equatorial bonds. But in this complex, the CuO bonds are equal. Why they are equal? The reason behind this is that there is rapid interconversion between the distorted geometries. So rapid interconversion between distorted geometries means that the deviation from the regular octahedral geometry that occurs very rapidly. So the bond length also change from regular to irregular, longer or shorter, very rapidly. The bond lengths change, and this change in bond length, since it occurs very rapidly, so on the experimental time scale, these are averaged out, that is time averaged. And because of this time averaged distortion on the experimental time scale, so when we are measuring using experimental techniques the geometry of the compounds, like for example if we use X-ray technique, then because of this time average, all the bonds remain appear to be equal. So all metal ligand bonds, there is no difference, they appear to be equal. Although they are not equal, these bonds appear to be equal, and this is actually known as dynamic Janteler distortion. So in the theoretical part, you must have learned about the static and dynamic Janteler distortion. So what happens in static? In static, this unequal bond length remains the same, but in dynamic, there is rapid interconversion between different distorted forms, distorted geometries. So when it is experimentally measured, this is time averaged and they appear to be equal because of this rapid interconversion between different bond lengths. So what should be the correct option for this question? So option A says failure of the Janteler theorem to predict the structure of this complex. No, Janteler theorem does not fail to predict the structure of this complex. The second option says error in the crystallographic estimate of CuO distances. No, there is no error in the crystallographic estimate as well. Then option C says dynamic Janteler distortion of the CuO bonds. Yes, there is dynamic distortion of the CuO bonds that we observed right now. So, because of this rapid interconversion, that goes to the case of dynamic Janteler distortion. So, option C should be the correct answer. Let's read option D also, which says symmetrical distribution of the 9 valence electrons of Cu. No, absolutely not. Cu2 in the +2 oxidation state, copper shows an unsymmetrical distribution of the 9 electrons that we saw like this in the Eg orbitals. So ultimately option C is the correct answer, where we have a dynamic Janteler distortion of the CuO bonds leading to the appearance of all the copper oxygen bonds as equal. Okay, so I hope this explanation was clear, and it's quite an interesting question in terms of Janteler distortion, and I hope this explanation was clear and hope it is helpful. Please like, share and subscribe if you find my videos helpful, and please let me know in the comment section what you want to learn next in chemistry. Thank you so much.